So I want to thank for the invitation. So it's only my second talk over Zoom. The first one went pretty bad because I used slides, and I think I had an hour, 1 hour talk, and I think I finished after 40 minutes. So I was going super fast. So I'll try something different this time, which is I'll simply write as if I had a blackboard. So hopefully it will work out better. So what I'm gonna do first, I'll just do a brief survey of some of the recent results on minimal surface, and then I will talk about some new directions that I'm developing with Fernando Marques and also with Danny Calgary. So let's start the introduction. So I'll just briefly define what a minimal hypersurface is. So minimal hypersurface contained on a closed manifold with respect to symmetric G is a critical point for the area functional. Area functional. So the most basic question one can ask regarding minimal hypersurface is whether they exist or not. And so this was asked by Yalls in '92 and became known as Yalls conjecture. And the question is, does every closed three manifold with a Riemannian metric admit infinitely many closed minimal surface? So Yalls' motivation to ask this question was that minimal surface that can be seen as a higher dimensional analog of geodesics. And since the 1920s, when Birkhoff showed that on every, actually, yes, so I think 1910 or 1912, where he showed that on every sphere with any metric can always find a closed geodesic, then there was a huge amount of research done on the existence of closed geodesics, and eventually it was proven that on every surface you can always find infinitely many distinct closed geodesics for every metric. So motivated by all these developments, I think Yalls conjectured that the same thing should happen for minimal surface. The big difference between minimal surface and geodesics is that geodesics, they are a very peculiar object because they can be defined in two different ways. On one hand, they can be defined as critical points for the length functional, in the same way that I'm defining here a minimal hypersurface as critical points for the area functional, but they can also be defined as closed periodic orbits to the geodesic flow, which is a Hamiltonian flow. And so in the proof, in the massive amount of work that has been done on the existence of geodesics, both perspectives have been widely used. And so the interest of Yalls' conjecture is that can we prove that just using the variational approach, can we still prove that on any manifold you can find an infinite number of minimal hypersurface? So that would be like the philosophical interest. So then for many years, the best result known was due to Shane Simon and Pitts, which showed that you can always find at least one. And then in the last years, there have been a tremendous development on this question. So I'll just go through some of the recent developments. Okay, so the first one, this was due to Fernando Marquez and myself in 2014, and we show that if okay, let's make a caveat here. Let me erase this to make the presentation easier. Let's assume this. I'll write it in blue. So from now on, Mn-1 is orientable, and there's a restriction on the dimension. The dimension is between 7 and 3. Okay. Okay, so now we can start. So the result I was mentioning that was due to Marquez, Fernando, and myself is that if you take a manifold with positive Ricci curvature, then indeed you can find infinitely many. Then I'll just write this: there exists infinitely many closed minimal embedded hypersurface. Okay. The developments kept occurring, and so 3 years ago, jointly with Erie, Fernando Marquez, and myself, in 2017, we showed that for C infinity generic set of metrics, the union of all closed minimal let me pass here, closed minimal embedded hypersurface in the manifold with respect to this generic metric is dense in the manifold. In particular, Yalls conjecture will hold in the generic setting. Yalls conjecture holds generically. So by C infinity generic set, it's in the bare category sense. So the important properties is that if you intersect that set of metrics with any other generic set, you still get a generic set. And if you pick any metric and choose some epsilon, you can find a metric which belongs to that set as within and is within epsilon away in the C infinity topology from the metric you pick. So then 1 year later, there was another development, this due to Marquez, Neves, myself, and Antoineson. And here, I'll just state this, not 100% precisely. You can see the paper for the details. I'll just state that, again, for a generic set of metrics, for a C infinity generic set of metrics, there is a sequence of minimal embedded hypersurface. They are all closed and smooth. So let me just say minimal hypersurface to mean something that's a closed, smooth, minimal embedded hypersurface. there exists a sequence of minimal embedded hypersurface that becomes equidistributed in M. In the ambient manifold. And then in the same year, Song he showed that every manifold has infinitely many minimal embedded hypersurface, minimal hypersurface. They are all, again, closed, smooth, and embedded, minimal hypersurface. In particular, what this result means is that Yalls conjecture holds now for every metric. Thus, in particular, Yalls conjecture holds for every metric. Okay, and so it's worthwhile to stop a bit here, because if we, again, the first result on existence of closed geodesics, that was due to Burkhoff, I think in 1912. And then there was a tremendous amount of work. And in the early 90s, that was when Franks and Bangert, and then 1 year later, using a different way, Nancy Inkster, where they showed that every two-sphere admits infinitely many closed geodesics. So in the geodesics world, there was a period of maybe 80 years from the first result until we were able to prove the existence of infinitely many. Now, regarding Yalls conjecture, I find it remarkable then that since the first result of Fernando and I, which was in 2014, until the solution of Yalls conjecture, which was due to Antoine Song, that took only about 4 years, because this has been a period where there has been a tremendous development and tremendous work on the existence problem for minimal hypersurface. And so let me just mention now some more modern, okay, so there was another one, and then I'll mention the more modern development. So here again, so last 2 years ago, Antoine solved the Yalls conjecture. And then last year, there was another important development, which was due to Shinzu, where he proved what we call the multiplicity one conjecture. So I'm not going to write this, but I'll just explain by words what it means. So a common problem in finding geodesics or in finding minimal surface is that multiplicities are allowed. For instance, in the problem of geodesics is to get the same curve just travel twice, or if we think of a geodesic as a periodic orbit, will just be twice the period, right? And so the same thing occurs for minimal hypersurface. You produce them using a variational method, which is called min-max theory, but then there's always the problem that you can get a minimal surface with multiplicity 2 or 3. So Fernando and I, we conjectured that generically multiplicities should not occur. And the reason why we were interested in that conjecture is because, as it is often so, the problem of multiplicities, it's one of the key problems in geometric analysis that prevents the theory to be developed further as if it was just a finite dimensional theory. For the case of minimal surface, the general picture is we think of minimal surface as critical points for the area functional. And so the general finite dimensional theory one could use is Morse theory, which relates the topology of the space with the number of critical points that a Morse function has. And so this picture, so this translation between the infinite dimensional setting for minimal surface and the ideas for Morse theory, the main technical issue that is preventing from having just a straightforward translation from one to the other is the issue of these multiplicities. Okay? And so Shinzu he proved the multiplicity one conjecture, which philosophically what it implies is that from the point of view of Morse, which implies is that for a generic metric, we can think of the area functional as just a Morse function on a finite dimensional space, and the results you expect for finite dimensional space, they can be translated into results for minimal hypersurface. So I will write one consequence of the Shinzu's proof of the multiplicity one conjecture. So so this uses Shinzu multiplicity one conjecture, which was from 19, and then some work by Fernando and I, Marquez and Neves from the same year. And the result is that if the metric is bumpy, is a bumpy metric, and what this means is that every critical point is non-degenerate, or in the language of Morse theory, that the area function is a Morse function, is a bumpy metric, i.e. area functional is Morse. Is Morse. Then for every integer k, there is sigma k, a minimal hypersurface, again closed and embedded, a minimal hypersurface with Morse index k. Moreover, the area growth of this minimal hypersurface obeys a Weil law. Moreover, the area growth of sigma k obeys Weil law. And what this means is that if I look at if I divide the area of sigma k over the n plus 1 root of k, and I make k go to infinity, we're going to get some universal constant alpha n, and then of course some scaling of the volume. Okay, but the point is that this is universal. Just depends on the dimension, just like similar to what obtains in the Weil law. And now let me mention one more result. And so let me mention a question, okay, or a remark, which I think it's interesting, is that there's, say, a generic manifold should have many more minimal surface than the ones given by this theorem. So let me write this. Any manifold, oops, let me not write in there. Any manifold should have at least many more minimal surface than the ones given by the result above, But the overall picture is not clear yet. So or let me state this as a question. Can we characterize characterize all minimal surface in the generic case, all minimal hypersurface in the generic case, So let me present you a result that just from some month ago due to Antoine Song and Shinzu that shows the interest of the question, but gives evidence that indeed we should have many more minimal surface on any given closed manifold than the ones given by this previous result. So let me state this here. So this is due to Antoine Song and Shinju. This is from some month ago. And the setup is the following. For a generic set of metrics, if we take some closed Riemannian manifold having orientable Morse index, orientable minimal surface of Morse index 0, orientable minimal hypersurface of Morse index 0. Let me draw a picture here. So this would be the manifold. Okay, and let's call the minimal, this Morse index 0 minimal hypersurface will be this one. So this is Morse index 0. So Morse index 0, it means that it's a local minimum for the area functional. So indeed, if we perturb this red minimal surface there, at least if we judge it from the picture, we can imagine that the area will only go up. So we take a minimal surface, a minimal hypersurface, that's a local minimum for the area functional, and then their result says that there is a sequence of minimal surface, a sequence of minimal hypersurface, let's call it Li. And now you can see the exact statement in his paper here. I'll just describe it heuristically. That spirals towards sigma. I'll draw a picture. That should be convincing. Towards sigma. So the picture of Li will be something like this. So if it were a geodesic, we can imagine a geodesic, a closed geodesic, that is gonna spiral towards sigma, but becomes closed. Okay, so this would be the Li. In particular, their area goes to infinity, their Morse index goes to infinity, but the ones given by this result of Shinzu and myself and Fernando, those we expect that should become equidistributed. So in particular, they should not be the ones that are given by the Song and Zhu result, but it would be interesting to say, look at take a sequence of minimal surface whose index and area goes to infinity. What can you say about their limit or their closure? Or can we have any characterization of the limiting set, any meaningful characterization of the limit set? Okay, so any questions? Okay, I guess not. So what I'm going to do now is I will describe some new directions regarding existence of minimal hypersurface. So let me say, okay, so here it's worthwhile to go through what happens in the geodesic case to give some intuition of the things we are after. But the general motivation is that any closed tree manifold should have a lot of minimal surface. I would expect many more than the ones described by this result of Fernando and myself, and of that falls from the multiplicity one conjecture of Shinzu. And the idea is, can we try to have a handle or have a possible characterization of the limiting behavior of minimal hypersurface? An interesting case to study, of course, is the case of negatively curved manifolds, because those should be the ones which have the highest number of minimal hypersurface, so where the variety is bigger. Okay, so let me so let's set up some notation here. So for the rest of the talk, I'm considering the case where the tree manifold, we put the metric G such that it's negatively curved. The metric has negative curvature. So which means from geometrization, we know that the tree manifold has to be the quotient of hyperbolic space by some lattice, where gamma is a subgroup of the orientation preserving isometries of H3, which is PSL2C. Okay, let's also, from now on, we denote by G minus 1 the hyperbolic metric. Hyperbolic metric on M3. Okay, so let me remind a celebrated result regarding the behavior of geodesics in negatively curved manifolds. So let's consider this quantity. It's called the entropy. And this is the, we look at, we count the number of closed geodesics of length less or equal than L. Closed geodesics, gamma, with length less or equal than L. And we count them all. We take the log and we divide by the growth power, and then we make L go to infinity. And we get a number. Of course, we should take the lim sup or the lim f, but it was shown by Margulis that this number is well defined. So that's part of the process of the next theorem I'll state. So the celebrated theorem, so this follows from the joint work of, from combining the works of Margulis, this I think was his thesis from 69, then Manning from 79, and then finally Besson, Courtois, and Gallo from 95. And what the theorem, one way we can state the theorem is that assume the volume, let's make a normalization, which is that the volume is 1. Then the result says that the entropy is minimized by the hyperbolic metric, and it's equal to the hyperbolic metric if and only if the metric is the hyperbolic metric. Then the entropy is minimized by the hyperbolic metric and equality if and only if G is the hyperbolic metric. So the result holds in a much more general setting. So the manifold does not need to be a tree manifold. I think it needs to be, so the manifold just needs to admit a locally symmetric metric, and then the result will be true where the locally symmetric metric is the one that minimizes the entropy. Okay. So the question I'll talk about for the next 50 minutes is whether similar rigidity holds for minimal surface. So similar characterization for minimal surface. Okay. So before we do this, so the difficulty comes from the fact that if we compare geodesics on hyperbolic surface with minimal surface on hyperbolic manifold, there are way more minimal surface on hyperbolic manifold than geodesics on a surface. And the reason why I say this is that, so let me just write a remark. And so let me just say this. So minimal surface in, let's take that manifold with the hyperbolic metric, they aren't necessarily, and now I'm going to have to move this side. So let's see if you can fit everything in the picture. Almost, that's like this. So unique in their homotopy class. Or homologically non-trivial. Or of Morse index 0. So these are all attributes which hold for geodesics on negatively curved manifolds. So it's well known that if you take a negatively curved metric, geodesics, they are all local minimums for the length functional, and they are actual global minimums for the length functional in their homotopy class. So for negatively curved manifolds, there's a one-to-one correspondence between the homotopy group and the geodesics. In minimal surface, it's not like that, because you can have many minimal surface which are homologically trivial, and even in the same homotopy class, you can have many minimal hypersurface. Of course, you have the area minimizing homotopy class, but then you also have you can also have minimal surface which are unstable critical points within that homotopy class. So there are known examples of minimal surface satisfying either of these three things. So there are more minimal surface than geodesics. So if you want to get this rigidity result, it's important that we find a suitable class of minimal surface to work with. And so that's what I'm going to find now, is to tell you what is the class that among all minimal surface, what is the class of minimal surface I am considering. Okay, so for this, I need to introduce some more notation, which is, let's consider pi homotopy class of pi 1 injective minimal surface, and this is also known as essential minimal surface, sorry, not minimal, surface in the manifold. So this would be the analog of taking a homotopy class of curves. So here we take a homotopy class of pi 1 injective surface. And so there's the notion of, now I want to define what is the limit set of pi. I want to say what is the limit set of pi. So what I wrote was, okay, so let's just step back 2 minutes. What I'm going to do in the next 5 minutes is to identify a class of minimal surface to which we want to work with, and so the minimal surface will work with. They will all be area minimizers in their homotopy class, but I will not consider all possible homotopy classes. I will consider a subset of those homotopy classes, and this is what I'm going to explain now. So I started just setting up the notation of taking pi homotopy class of pi1 injective surface on the closed manifold, and now I want to define what is the limit set of this homotopy class. Okay, so let me explain what this is. So we take an element in the homotopy class. So let's do a picture. Here's the surface. Here's the hyperbolic manifold. Let's just M3, which is H3 mod by gamma. And now I take an element which is non-trivial in homotopy. Could be the sigma. It's a surface whose fundamental group injects, and you cannot shrink it to a point. And now let's lift sigma to the universal cover. So we know there's a map here from the universal cover, which will be H3, that projects onto M3. And let's take D to be lift of sigma to H3. So because sigma is pi1 injective, the lift is a disk. So when we do this, we're going to get a disk. So here I'm using the unit ball as the model for the hyperbolic space, and we get some disk there. So this would be D. Okay. So the limit set, this is by definition the intersection of the closure of D with the boundary at infinity of the hyperbolic model. So it's intersecting this disk we get with the boundary of H3, which can be identified with the two spheres. So the limit set is going to be this curve here. This is the limit set. Of course, the limit set might change if we choose another representative for sigma, but it will change only up to conjugacy. And so this is well defined up to conjugacy. This is well defined. Up to conjugacy. So if I change the representative sigma, this curve will just change by a conformal map of the two sphere. Okay? And so this curve, it's characterizes somewhat the homotopy class pi. Okay? And so let me state a result in that direction, which is an old theorem of Bowen from 79. And Bowen theorem, what it says is that this limit set, this red curve, is smooth, or its Hausdorff dimension is 1, if and only if the homotopy class pi admits a total geodesic surface. So this is so typically this limit set will not be a smooth curve. It's a fractal-like Jordan curve. So the Hausdorff dimension, let me write this carefully. The Hausdorff dimension as this limit set is 1, if and only if pi contains a totally geodesic surface. In the homotopy class. Now, the reason why this is very special is because it's known that there are many hyperbolic manifolds for which that is never the case. So the more likely than not, the limit set will never be a smooth curve. Okay, and if it's a smooth curve, it has to be a round circle. Okay, so now let me say introduce the last definition, which is S epsilon m. So now I look at all homotopy classes such that the Hausdorff dimension of the limit set is between 1 and 1 plus epsilon. So this is homotopy classes pi, where the Hausdorff dimension of the limit set is greater or equal than 1 and below 1 plus epsilon. So these are all homotopy classes which for which the minimal representative with respect to the hyperbolic metric should be close to a total geodesic surface. And so of course this set could be empty, but so let me make two remarks. So the first remark is that there are known examples. This is due to Alan Reed, the first example, if I'm not mistaken, known examples where this set is empty, where you never have a homotopy class whose Hausdorff dimension of the limit set is exactly 1. But the second remark is a theorem of Kahn-Markovich from some years ago, and it says that the set we consider has infinitely many elements for any epsilon positive, and they actually count them in some suitable way. Is that for all epsilon positive, the cardinality of this set has always infinitely many elements. Okay, so now having these ingredients, we can state the result. So given homotopy class, we define the area of that homotopy class to be the area of the minimizer in the homotopy class. So this is just one definition. We define the area of pi g as being the infimum of the area of sigma. Okay, so what I explained was that there are many cases where you'll have no homotopy class whose limit set is a circle, but if you allow for the limit set to be a fractal-like curve whose Hausdorff dimension is not too far away from 1, then you always have infinitely many elements. So this is a famous result of Kahn-Markovich. Okay, and so now in doing this, I was defining, given a homotopy class, I'm defining what is the area of that homotopy class, which is just the area of the least area minimal surface in that homotopy class. So we just minimize the area of sigma among all sigma in the given homotopy class, and of course this number depends from the metric G. And so let me state the theorem now, which is due to Caligari, Fernando, and myself from this year. And so the theorem is that consider the following entropy type quantity. We define as G to be, we take the limit when epsilon, so we'll make epsilon get smaller and smaller, and then we make L get larger, and so we mimic the quantity for geodesics. We take the log of the cardinality, and now we count all homotopy classes whose area is below 4 pi L minus 1, where pi is one of these homotopy classes whose Hausdorff dimension of the set is very close to 1. And then we divide this by L log L. And so the result is that this quantity is always less or equal than a classical quantity for negatively curved spaces, which is known as the volume entropy. So I'll just write that. It's less or equal than the volume entropy of G. And now we have to make it scale invariant. So the volume entropy scales like length. So we square it. And we put a factor of 2. And the second result is that we normalize the metric so that the sectional curvature assume of G is less or equal than -1. Then this entropy is minimized by the one for the hyperbolic metric with equality if and only if the metric is the hyperbolic metric. Okay. So let me just finish with 2 questions in this direction. And so let me just say questions. So the first one is whether on 1 we can replace 2 by 1/2 so that it's optimal. Is this counting number for minimal surface less or equal than the volume entropy of G squared divided by 2 as opposed to twice? So the number 2 there, then it's not optimal for the hyperbolic metric. And the second question is, can we replace this condition by just sectional curvature, by scalar curvature less or equal than 6? Can we replace suffices to assume scalar curvature less or equal than -6? Okay, so I'll just stop here. Okay, so I apologize for the loss of connection and thank you so much for your time.